Imagine standing under a canvas of a million stars, gazing up at the enigmatic expanse of our universe. What if you could see beyond the shimmering veil of Earth's atmosphere, past the distortions caused by turbulent air, and witness the cosmos in breathtaking, crystal clear detail? For centuries, humanity has dreamed of such a view. Ground-based telescopes, even the most powerful ones, are inherently limited by our planet's atmospheric conditions. The very air we breathe, with its clouds, light pollution, and thermal currents, acts as a blurry filter, obscuring the true magnificence of distant galaxies, nebulae, and stellar nurseries. This constant struggle for clarity fueled a revolutionary idea, a vision that would fundamentally transform our understanding of everything beyond our blue planet. It was a bold proposition, one that seemed almost impossible given the technological constraints of its time, but it ignited a spark that would eventually lead to one of humanity's most incredible scientific achievements. This is the story of a telescope that dared to defy gravity, a vision elevated into the silent, pristine vacuum of space, forever changing our cosmic perspective. The year was 1946, a time when rockets were still nascent technology and the idea of space exploration was largely confined to the realm of science fiction. Yet, an astrophysicist named Dr. Lyman Spitzer Jr. dared to envision something truly extraordinary, a telescope not bound by Earth's atmosphere, but orbiting high above it. His reasoning was simple yet profound. By escaping the atmospheric blur, a space-based telescope could provide images of unparalleled clarity, revealing secrets of the cosmos that were previously inaccessible. It sounds logical now, but at the time, this was a radical, almost fantastical concept, preceding even the first successful rocket launches into outer space. Spitzer's unwavering conviction, however, planted the seed for what would become one of the most iconic scientific instruments in history. His persistent lobbying, especially as the U.S. space program matured through the 1960s and 70s, laid the groundwork for a monumental collaboration that would soon bring this ambitious dream to fruition, turning a theoretical possibility into a tangible reality that would redefine our cosmic landscape. The journey from Dr. Spitzer's audacious proposal to the launch of an actual space telescope was long and arduous, spanning decades of scientific planning, political negotiation, and engineering marvel. In 1975, a pivotal collaboration began to take shape, uniting the scientific prowess of the U.S. National Aeronautics and Space Administration, NASA, with the burgeoning European Space Agency, ESA. Together, these two powerhouses began drafting the initial intricate plans for what was then simply known as the Large Space Telescope. 2 years later, in 1977, a significant hurdle was overcome when the U.S. Congress, recognizing the immense potential of such a project, approved the necessary funds, transforming the vision into a concrete program. The critical task of construction and assembly was entrusted to Lockheed Missiles, now Lockheed Martin, a company renowned for its aerospace expertise. This colossal endeavor culminated in the telescope being named after a giant of astronomy, Edwin Hubble. His groundbreaking observations of variable stars in distant galaxies had provided irrefutable evidence that our universe was not static but expanding, lending crucial support to the revolutionary Big Bang theory. The name Hubble thus became synonymous with profound cosmic discovery, a fitting tribute for an instrument destined to expand humanity's gaze further than ever before. After years of meticulous planning, complex engineering, and a heartbreaking delay following the Challenger disaster in 1986, the Hubble Space Telescope finally soared into orbit. On April 24, 1990, tucked securely within the payload bay of the Space Shuttle Discovery, Hubble embarked on its much-anticipated journey to the stars. The world held its breath, ready for the unprecedented images this bleder 1.5 billion eye in the sky promised to deliver. However, the initial euphoria quickly dissolved into widespread disappointment and dismay. Almost immediately after its deployment, astronomers discovered a critical and devastating flaw. Hubble couldn't focus properly. The images it transmitted back to Earth were disappointingly fuzzy, a stark contrast to the crystal clarity that had been promised. The very reason for putting a telescope in space, to escape atmospheric distortion, seemed to have been undermined by a fundamental error within the instrument itself. This wasn't just a minor glitch, it was a profound failure that threatened to render the entire mission, years in the making and billions of dollars spent, a monumental scientific tragedy. The dream of unparalleled cosmic vision had, for now, become a blurry nightmare, leaving scientists scrambling for answers and a solution to this astronomical embarrassment. The heart of Hubble's problem lay in its primary mirror. This colossal, meticulously crafted piece of glass, designed to gather light from across the cosmos, had been ground to an infinitesimally incorrect dimension. The error, shockingly precise yet catastrophic in its effect, was equivalent to 1/50th the thickness of a human hair. While seemingly minute to the uninitiated, this microscopic deviation introduced a severe optical distortion known as spherical aberration. In simpler terms, instead of bringing all incoming light rays to a single, sharp focal point, the flawed mirror caused light reflecting from its edges to converge at a different point than light reflecting from its center. The result was not a crisp, singular image, but rather a hazy, overlapping blur that robbed celestial objects of their intricate details. For the astronomers and engineers who had dedicated their lives to this project, the fuzzy images were agonizing. They had not spent years designing and building this marvel of engineering just to be satisfied with mediocre snapshots of the universe. The precise measurements and breathtaking clarity they had envisioned were simply unattainable with this fundamental defect, presenting an unprecedented challenge that demanded an equally unprecedented solution, lest Hubble be relegated to an orbiting monument of unfulfilled potential. Faced with the profound disappointment of a flawed telescope, NASA scientists and engineers embarked on an audacious plan, a space-based repair mission. They conceived of COSTAR, the Corrective Optics Space Telescope axial replacement, essentially a contact lens for Hubble's defective vision. COSTAR was a complex instrument consisting of several small, precisely crafted mirrors designed to intercept the light beam from the flawed primary mirror, correct the spherical aberration, and then relay a perfect focused beam to Hubble's scientific instruments. This mission, scheduled for December 1993, would be one of the most challenging and high-stakes space endeavors ever attempted. For 11 grueling months, NASA astronauts and ground crews meticulously prepared, rehearsing every intricate maneuver. Finally, 7 brave astronauts aboard the Space Shuttle Endeavour rocketed into space, embarking on a week-long odyssey of spacewalks. With incredible precision and perseverance, they installed COSTAR, a testament to human ingenuity and determination. When the telescope was retested after these heroic repairs, the transformation was astounding. The images, once blurry and indistinct, were now breathtakingly sharp and clear. Today, all instruments added to Hubble have built-in corrective optics, making COSTAR itself obsolete, but its legacy as the spectacles that saved Hubble endures, ushering in an era of unparalleled cosmic discovery. Beyond its remarkable journey and dramatic repair, the Hubble Space Telescope is a masterpiece of optical engineering, built upon the principles of a specific type of instrument, the Cassegrain reflector telescope. Unlike refracting telescopes that use lenses, Cassegrain reflectors employ mirrors to gather and focus light. For Hubble, light from distant celestial objects enters through its open end, traveling down its long tube. The first point of contact is the massive primary mirror, measuring 7.9 feet, 2.4 meters in diameter, which gathers this faint light. This primary mirror then reflects the light upwards to a smaller secondary mirror, just 1.0 foot, 0.3 meters in diameter, positioned closer to the telescope's entrance. The secondary mirror, in turn, reflects the light back down through a precise hole located in the center of the primary mirror, converging it at a focal point behind the primary mirror. If you were to trace the path of light, it would resemble a W shape. These aren't just ordinary mirrors. They are crafted from glass and meticulously coated with ultra-thin layers, 3/millionths of an inch of pure aluminum and 1/millionth of an inch of magnesium fluoride. This specialized coating enables them to efficiently reflect not only visible light, but also the invisible wavelengths of infrared and ultraviolet light, significantly expanding Hubble's observational capabilities and offering a broader spectrum of cosmic information to scientists. Once the light has been expertly gathered and focused by Hubble's mirrors, it is then distributed to a suite of highly specialized scientific instruments, each acting as a unique eye to perceive different facets of the universe. One of Hubble's most critical imaging tools is the Wide Field Camera 3, or WFC3. This powerful instrument significantly extended Hubble's observational reach, featuring 2 distinct channels designed to capture both ultraviolet and infrared light. It uses 2 separate rectangular chips for its UV visible and infrared observations, coupled with an extensive array of filters that allow astronomers to isolate specific wavelengths. This versatility enables WFC3 to glean intricate details about celestial objects, from the formation of stars in nearby galaxies to the very distant early universe. Equally vital is the near-infrared camera and multi-object spectrometer, NICMOS. Often dense clouds of interstellar gas and dust obscure our view of celestial objects in visible light. NICMOS, with its three sensitive cameras, ingeniously bypasses this cosmic camouflage by detecting the infrared light or heat emitted by these hidden objects. This allows astronomers to peer into dusty star-forming regions, observe the birth of planets, and study the cores of galaxies, revealing phenomena that would otherwise remain shrouded in cosmic mystery, effectively making the invisible visible. Beyond simply capturing images, Hubble's instruments are designed to meticulously dissect the light arriving from the cosmos, revealing an incredible wealth of information. The Space Telescope Imaging Spectrograph, or STIS, serves as Hubble's cosmic prism. Just as a prism separates white light into a rainbow of colors, STIS splits the incoming light from a celestial object into its constituent wavelengths, forming a spectrum. By analyzing this unique chemical fingerprint, scientists can determine an object's precise chemical composition, what elements are present and in what quantities. But STIS reveals even more. The spectrum can also convey the object's temperature, density, and even its motion. If an object is moving towards us, its light shifts slightly towards the blue end of the spectrum. If it's moving away, it shifts towards the red, a phenomenon known as the Doppler effect, providing clues to the universe's expansion. Though STS temporarily lost power in 2004, it was successfully repaired in 2009. Complementing this detailed analysis is the Advanced Camera for Surveys, or ACS. Installed during a servicing mission in February 2002, ACS dramatically doubled Hubble's field of view. Seeing primarily visible light, ACS was designed for broad surveys, mapping the elusive distribution of dark matter, detecting the most distant objects in the universe, searching for massive exoplanets, and examining the complex evolution of galaxy clusters. Although two of its three cameras were disabled by an electrical short in 2007, ACS continues to provide invaluable insights to truly unlock the universe's secrets. A telescope must not only have powerful eyes, but also incredibly steady hands. This is where Hubble's Fine Guidance Sensors, or FGSs, come into play, three extraordinary instruments crucial for both precise pointing and subtle scientific measurements. When Hubble targets a celestial object, two of these FGSs actively work in tandem to keep the telescope fixed on its mark. They achieve this by locking onto guide stars, relatively bright stars located within their respective fields of view, close to the primary target. Once a guide star is acquired, the FGS continuously monitors its position, feeding incredibly precise information back to Hubble's steering system. This feedback loop ensures that the telescope remains absolutely motionless and perfectly aligned with its intended target, counteracting any minute drifts or vibrations. While two FGSs are dedicated to this critical pointing function, the third FGS is freed up to perform another vital task, astrometric measurements. This involves precisely measuring the positions and diameters of stars and even the minute separation of binary star systems. Crucially, these astrometric measurements are fundamental for detecting exoplanets. As planets orbit their parent stars, their gravitational pull causes the star to wobble ever so slightly across the sky. By detecting these tiny wobbles, the FGSs provide powerful indirect evidence of planets orbiting distant stars, showcasing their dual role as both navigators and discoverers. While we often think of Hubble solely as a telescope, it is, in fact, a sophisticated spacecraft, complete with all the necessary systems to survive and operate in the harsh environment of space. Like any independent satellite, it requires a robust power source and reliable communication channels to Earth. The lifeblood of Hubble's operations is electrical power, generated by two expansive solar panels that extend like wings from its main body. Each of these remarkable panels can convert the sun's energy into an impressive 2,800 watts of electricity, powering all the onboard instruments, computers, and various systems. When Hubble inevitably passes into Earth's shadow where sunlight is unavailable, its operations are sustained by onboard batteries that can provide power for up to 7.5 hours, ensuring continuous observation. Beyond power, communication is paramount. Hubble must constantly talk to controllers on the ground, relaying the vast quantities of digital data it collects and receiving new commands for its next celestial targets. This vital link is maintained through a sophisticated network of relay satellites known as the Tracking and Data Relay Satellite (TDRS) system. Currently, 5 TDRS satellites orbit Earth, strategically positioned to ensure continuous contact. 4 antennae on Hubble transmit and receive this information, with two main onboard computers managing the process, one dedicated to ground communication and the other overseeing steering and crucial housekeeping functions, all backed up by redundant systems for emergencies. This intricate web of power and communication allows the scientific bounty of the cosmos to flow seamlessly from space to our eager minds on Earth. Hubble's extraordinary ability to capture images with unparalleled clarity is even more remarkable when one considers its orbital acrobatics. This massive observatory is not stationary. It zips around the Earth at incredible speeds, completing a full orbit approximately every 97 minutes. Keeping such a rapidly moving platform precisely fixed on a distant target is a monumental engineering feat achieved through a sophisticated interplay of three onboard systems: gyroscopes, the fine guidance sensors FGSs we discussed earlier, and reaction wheels. The gyroscopes act as Hubble's internal compasses, meticulously tracking its every gross movement. They sense any deviation from the desired orientation, instantly relaying this information to the telescope's flight computer. The flight computer then performs rapid calculations, determining precisely how much and in what direction Hubble needs to adjust to return to and remain on target. This calculated correction is then translated into commands for the reaction wheels. These wheels, spinning at varying speeds, exert torque on the telescope, subtly changing its orientation without the need for propellants, offering incredible precision and longevity. Meanwhile, the FGSEs provide the ultra-fine tuning. Two of these sensors continuously lock onto guide stars around the target, feeding real-time positional data to the flight computer. This ensures that the guide stars remain within their field of view, effectively creating a virtual anchor that keeps Hubble's gaze unwavering, allowing for the stable, long-exposure observations that have become its hallmark. Together, these systems form a symphony of control, ensuring that Hubble's eye remains perfectly still. Since its successful repair, the Hubble Space Telescope has utterly transformed our understanding of the cosmos, earning its place as one of the most successful scientific instruments in human history. Its clear-eyed findings have not only confirmed existing theories, but have also unveiled entirely new phenomena, reshaping our cosmic view. Thousands of scientific papers have been published based on Hubble's data, providing unprecedented insights into fundamental questions about the universe. It has precisely measured the age of the universe, offering a more accurate timeline for cosmic evolution. Hubble has allowed us to peer into the hearts of gigantic black holes, observing their powerful jets and studying their influence on galaxy formation. Its iconic images have revealed the spectacular beauty and complex processes of star birth and death, capturing dying stars in their final brilliant throes and witnessing the genesis of new stellar nurseries. Beyond these, Hubble has provided compelling evidence for the existence of dark energy, the mysterious force accelerating the universe's expansion, and has mapped the distribution of dark matter, the invisible scaffolding upon which galaxies are built. Its observations of distant galaxies have offered glimpses into the universe's early history, showing us what the cosmos looked like billions of years ago. Hubble hasn't just shown us what's out there, it has fundamentally altered our place within the vast, intricate tapestry of space, inspiring generations and forever expanding the horizons of human knowledge. Even after more than 3 decades in orbit, the Hubble Space Telescope continues its tireless vigil, offering fresh perspectives on our dynamic universe. Though it has faced challenges and outlived its initial design life, its remarkable resilience and the dedication of the teams on Earth have ensured its ongoing legacy of discovery. While Hubble has provided a window into the visible and near-infrared universe, the torch of space observation is being passed to new generations of observatories, such as the James Webb Space Telescope, designed to explore even deeper into the infrared spectrum, promising to reveal even more profound secrets. Yet Hubble's contributions remain invaluable. It not only paved the way for these successors, demonstrating the immense power and necessity of space-based astronomy, but it also continues to complement their work with its unique capabilities. Its iconic images have not only advanced scientific understanding, but have also captivated the public imagination, making the wonders of the cosmos accessible to everyone. The Hubble Space Telescope stands as a towering testament to human ingenuity, perseverance, and our insatiable curiosity. It reminds us that even when faced with monumental challenges, the pursuit of knowledge can lead to extraordinary triumphs, forever expanding our vision and inspiring us to look up, wonder, and continue our endless journey of discovery among the stars.